All right, so the very first thing we're going to look at is section 1.1, and we're going to go through it kind of quick, mostly review stuff, just to kind of make sure certain terms, properties, distributive, associative, commutative, we just kind of remember what those mean. A little bit of stuff with the graphing calculator we might get to. If not, we'll get to it on Thursday or Friday. So first, this is a diagram you've probably seen in like a little bit of Algebra 1, and then, yeah, actually this is all Algebra 1. Just kind of how the different number sets relate to each other. Okay, counting numbers, I'm not going to write all these definitions down, but I will say them. But counting numbers are the simplest kind of numbers you can have. And think about when you count. What number do you start with?
1.
1. And what's the next one?
2.
2. No 1.5, right? No fractions, no decimals, no 0, no negatives. So counting 1, 2, 3, 4, 5, 6, 7, 8. That's how we count. Whole numbers include one extra number that counting numbers don't. Anybody know what that number is?
0.
Includes 0. The reason why we need it is because certain operations don't work if you don't have 0. Here's a counting number minus a counting number. Right? 4, then 4, both counting numbers. The problem is if you subtract them, you get an answer that's not a counting number. So if all you know is counting numbers, you would have to put, I don't know, there's nothing. Well, okay, let's invent something. Let's invent the idea of nothing, and let's draw it like that, and we'll call it 0, and now that's the set of whole numbers. Okay? So really, each time we have a new set of numbers, it's just because we needed a way to represent a calculation. Okay? Same with integers. Well, 5 is a counting number. 12, it's also a whole number. 12 is a whole number. But the problem is when you do 5 minus 12, you can't do that. Not with whole numbers, right? Because whole numbers start at 0 and they go up. So we have to invent the idea of having even less than nothing. And that's where integers come in. And now you have negatives. So if you don't know integers, like if I gave that to somebody in first grade, 5 minus 12, I don't know what they'd write. Right? They don't know negatives yet. So what are they going to do? Well, we know negatives, and we call them integers. So once you have integers, adding, subtracting, and multiplying are fine. You can give me any integer and give me any other integer, and I can add, subtract, or multiply, and I'll always get an integer answer. Always. But there's one operation where we run into a problem. And what would that be?
Division.
Division. Can you give me an integer and another integer, and when we divide them, the answer is not an integer?
1 divided by 3.
Yep. Integer, integer. But the answer is not. That's impossible, right? If all you believe in is integers, you can't do that. You're saying take one object and divide it to 3 people. Well, I can't, unless I break it into pieces, right? And parts or pieces are a fraction of something. That's when we get into rationals. And for most everyday purposes, that's pretty much as complicated as numbers get for people. Like you might go to the store and you buy something for, $3.98. $3.98 of a dollar. Right? It's not exactly 3, it's not exactly 4, it's in the middle. You get gas. Most of the time, when I go, I just fill it up. So if I fill it, it comes out to whatever it comes out to. If I pay with a credit card, I don't really try to make it exact, just whatever it is. So rational numbers, fractions, decimals, if you're cooking, maybe you don't need 2 cups of flour, you don't need 3, you need 2 1/3 cups. It's right in the middle, it's a fraction. So rational numbers are basically numbers that can be written as a fraction. So a rational number is any number that you can write in the form a over b, where a and b are integers. So this is not really considered a fraction, 2.3 over 4.7. It'd be better to write it as 23 over 47. That's really as much as you could reduce that. The top and the bottom should be integers, okay? And the bottom Can't be 0. That's the only integer it can't be. So those are your rationals. Now, some of these number sets have symbols. Okay? I know rationals do, reals do, and integers do. And the symbol that you're going to see for rationals is kind of like a Q. So if you see this symbol, like if the directions in the book said, write all answers that are, and you saw that symbol, it means rational. Okay. Integers kind of looks like a Z with that double line in it. And R's, well, we haven't got there yet. I'll explain that when we get there. So these are the symbols for, that's the integers, that's rational. So rationals are numbers you can write as fractions. What do you think irrational is?
You can't write it as a fraction.
You can't, right? An example of an irrational number, any square root that's not a perfect square. Square root of 2. You cannot write that as a fraction, right? And you might think, well, is it maybe someday where we have the technology to write that as a fraction once we figure out more decimals? No. I can prove to you that we will never be able to write square root of 2 as a fraction, no matter what. I don't care if you get a more powerful computer, or I can prove it's impossible. Now, pi is another number that they think is irrational, at least as far as we've calculated. There's no real pattern to it, so they think pi is irrational. I'm not sure how to actually prove that one. Okay? I don't know how to prove that one. So together, you take all the numbers you can write as fractions, all the numbers that you can't, and that gives you real numbers. That's algebra 1. Okay? Everything you study in algebra 1 is a real number. Does anybody know, like when you get to algebra 2, what you add to this? You have reals, and then you have another kind of number. Yeah?
Imaginary.
Imaginary. That's not on this chart. Imaginary would be off to the side. Okay? So we don't talk about imaginaries right away. We will, but not yet. Okay. And the way that the system works is if you're inside one box, you're automatically another. Okay? And the way I think of it is, think of it as places. Think of it as like Boston and then getting bigger. Massachusetts, Northeast, United States. Okay? If you are in Boston, are you also in Massachusetts? Yeah. I mean, maybe there's another Boston, Kansas or something, but don't get technical. Now, if you're in Massachusetts, are you automatically in Boston? No. So it doesn't work the other way around. If you're a counting number, you are a whole number. But if you're a whole number, you're not necessarily a counting number. Okay? But if you think of it as places, one inside the other, it helps it kind of make sense. So I told you I'd show you that last symbol. And the last symbol is for real numbers. It looks kind of like a capital R. Okay, I kind of understand where that one comes from, R, reals. Q, kind of even understand that, because when you divide two numbers, what do you call it? Quotient, so maybe rational, fractions, quotient, Q, I don't know. Z for integers, I'm not sure. I don't know where that comes from. So, binary, or the prefix bi, right? Like bicycle, bifocal means 2. So, there are 4 operations in math that, basic ones, that require 2 numbers to do it. Like if I said to you to add 5. Add 5 to what? I need something else. Add 5 to 6, get 11? Okay. But in order to add, you've got to have 2 things. To subtract, multiply, and divide, you've got to have 2 things. Can anybody think of an operation in math where you only need 1 number? And actually, I had one up on the other screen. Yep.
Factorial.
Yep, factorial. That's an operation where you just need 1 number. Yep.
Absolute value.
Absolute value, you just need 1 number. Square root is the one I was thinking of that I had on the screen. To find the square root of 2, that's all you need. You don't need anything else. Okay, so we're going to look at a few just kind of basic properties. And just see if we remember what they are. These properties I write, I'm going to use the letters A, B, and C. And those three letters can represent any real number. Positive, negative, fraction, decimal, or zero. Let's start with closure. I think some of these other ones are probably a little more familiar. Closure is usually the one people are, closure. Closure is the idea that, like, if you add an integer to an integer, think about it, do you always get an integer? Would you ever get something that's not an integer if you add two integers? No. If you add two numbers that are not fractions, you're not all of a sudden going to get a fraction. So that's the idea of closure, is that what you started with two integers, you did an operation, and you got back the same type of number you started with, integer, right? Now think about subtraction. Let's pretend that we only know about whole numbers. If you subtract a whole number from a whole number, will you always get a whole number? No. What? Give me an example where that wouldn't work. Yeah.
Like when you did the 5 minus 12 earlier.
Yeah. So what we could say here is that subtraction is not closed under the whole numbers. Meaning you could start with a whole number minus a whole number and get something that's not a whole number. You kind of went outside the whole number bubble. You went somewhere else. That means it's not closed. How about multiplication? If you multiply a whole number times a whole number, do you get a whole number? Yeah. There's no way you can multiply two numbers that are not fractions and get a fraction. It's not going to happen. Okay? So we could say that multiplication is closed under whole numbers. Okay? Subtraction is usually the one that's a little tricky, and division. Okay? Commutative. What does it mean to commute? Like if you commute, or if two things are commuted.
Transported.
Yeah, they moved, went from one place to the other. So the commutative property for addition basically says we can add two numbers in any order we want. Basic algebra 1, pre-algebra, right? How about associative? Does anyone remember what that means? Think about associate. How do you associate? Like, when you think of like associate, what does that mean? Can you guess? Associate? Like, what does it mean for you to associate?
Relate? I don't know.
To what?
Relate?
To what?
I don't know. I don't
Yeah.
know.
To like get into groups.
Group, right? When you associate with someone, like if somebody said, you gotta stop associating with those people, I would think, all right, they don't want me to talk to those people, that group anymore, right? Or they're bad influence, whatever. So associate has to do with groups. And the way we group things in math is with grouping symbols. Could be parentheses, could be brackets, could be a fraction bar. Those are all grouping symbols. So doesn't matter if you've got three numbers and you add B and C first and then add A, or add A and B first and then add C. Try it with A1, B equals 2, and C equals 3. You'll get the same thing. Right? So again, that's the associative property for addition. How about identity? Anyone remember what that one means? What do you think of when you think of like identity? Identity is what? Like as a person. What is your identity? What does that mean? Well, no? Any guess? Your identity? What does that mean? What's your identity?
Who you are.
Who, what's the second word you said?
You.
You. You're talking about yourself, right? You. It's like you. So in math, you're talking about who you are, yourself. So an identity is basically what you can do to something to get itself back. It doesn't change it. That's who it is, right? This is who it was to start. It's the same thing when it finished. Its identity didn't change. It's the same. Right? So an identity is when you do something and get the same thing back. So for addition, that's add 0. Now, if I was doing the identity property for multiplication, would it be multiply by 0? What would it be for multiplication? 1. So the identity property would look a little different in multiplication. A times 1 equals A. All right. Inverse. What's another word for inverse? Yeah.
To like be the opposite of or turn it.
Yep, exactly. First thing you said, opposite. A, opposite A. For addition, if you take opposites and add them, you get 0. So that's the inverse property. It's what cancels something out. And the last one, most people are familiar with this one. Distributive. What operation does that have to do with? Multiplication, right? Just when you take and you multiply what's on the outside to the inside of parentheses. So all these properties I showed you, closure, commutative, associative, identity, inverse, they're all for addition. They have all the same properties for multiplication, and they're on page 2 in your book. Okay, I'm not going to write them all down, but like if you wanted to know what's the commutative property for multiplication, A times B equals B times A. That's the commutative for multiplication. The order changes. So there's 2 ways you could see a question on that, and I'm going to show you in the next example after we do this. Okay, so again, pre-algebra stuff. To have an equation, what do you have to have?
The equal sign?
Got to have an equal sign. It's a statement of, there you go, right there, equality. These are all equations. 2x equals 12. 3 plus 4 equals 2 plus 5, and 5 equals 2. Does anybody have any thoughts about any of those 3 equations? When you look at any of them, does anything come to mind?
One of them has x in it.
Okay, so that one has x in it, which is a what?
Variable.
A variable. So this is a conditional equation. Conditional equation. What does that mean? Well, it could be true. Depends. If you pick the right value for x, it'll be true. There's a condition to make it true. How about the other 2? Yeah?
The one on the right is completely wrong.
Yeah, this is a contradiction. It's a false statement. It's an equation, but it's not true. And how about the one on the left? Well, the bottom one on the left. Yeah?
The sums are equal.
They're equal. What's on the left equals what's on the right. And that is an identity. Okay? That's an identity. So 3 different kinds of equations. One that's always true, one that's never true, and one that could be true if you pick the right value for the variable. Okay, but they're all equations. So last thing before we look at an example, we'll look at 3 properties with equations that you've probably seen in geometry, but they all involve equations. And these are the properties. Does anybody think they know any one of those 3? First one says A equals A. Second one says if A equals B, B equals A. And the third one says if A equals B and B equals C, then A equals C. Anyone remember what any of those 3 are called? Yeah.
Wouldn't the second one be reflexive?
The second one be reflexive. Well, that is one of the words we're going to use. We have reflexive. Anyone think they know what the bottom one is called? Yep.
It starts with a T, right?
Starts with a T.
Transitive.
That's transitive. Let's look at it. So reflexive, I kind of think of reflexive as a reflection, right? When you have a reflection, you see the same thing back. So same thing on each side. So you're close. Symmetric is like if you write x equals 4, 4 equals x. Same thing, right? And then transitive, that property is used, can be used all over the place. Like you can use with parallel lines, like if A is parallel to B and B is parallel to C, then A is parallel to C. Right? So we use, I'm just showing you it with an equation. So the way you would see an example of something like this on a test is, well, could be one of two ways. I could list the properties on the left-hand side and basically ask you to show me the work. Or I could write the work and then you tell me what property I used. Let's try it that way. Let's go like this. What property did I just use right there?
Symmetric.
So symmetric would have been if I took all of this and put it on the right, and I took everything that was on the right and put it on the left. So not symmetric. Yep.
Distributive.
Distributive, yep. I did the distributive property.
Oh, I thought, never mind.
So I took that, basically I just went like this, which probably would have made it a lot more obvious if I did that. That's why I did it.
Okay.
So distributive property. Now, what about, let's see. Let's do let's go like this. What did I do on the left side? I just used another property. And I'm basically done now.
Transitive?
Not transitive. It's one of the first ones where I asked, like, what does it mean? And I asked about this word, and somebody said to go back and forth. Commutative. Yeah. So that was commutative. If you want to be specific, it was the commutative property for addition, not multiplication. And that's it. So you had the steps, and you had to figure out the property. Or it could be the other way around. Any question on that? So I'm not going to ask you, like, what's the definition of the distributive property. I might just say, simplify using the distributive property. So you just have to know what it means to do that. Okay. Coordinate system. All right, so number line, obviously positive numbers go right, negative numbers go left. The number right in the middle at 0, that's your origin. We'll go quick through that. So there's your inequality symbols. Less than or equal to, greater than or equal to. And once you give order to numbers, that's when you can use these symbols, right? Because now you're ranking numbers. You're saying, okay, this one is bigger than this one, right? Kind of giving them an order. Is there any questions on any of the inequality symbols? In Algebra 1, I would spend like a lot of time, we talk about alligators, bigger number eating smaller number, pre-calc. Okay. So when you graph on a number line, open circle, closed circle, right? At least that's one way to do it. If you have to graph something with a greater than or equal to, open circle, closed circle, greater than or just less than, that's your open circle. I kind of remember it like, if there's an extra line underneath, I have to do an extra step and fill in the circle. Okay. How many people have graphed inequalities using this way? Has anybody done it with parenthesis and bracket? It's another way to do it, which I may or may not, yeah. I'll talk about in a second. Right, let's just try an example. First thing is just understand this and this are the same thing. Which way do you think I would prefer if you could do either way? What do you think I would prefer?
First one.
Which one is that?
The x is greater than or equal to 2.
Yeah, why do you think do you know why I like that one better?
Because the variable's first.
And what happens if the variable is first? When you're reading it, it kind of tells you something. You know what it tells you when you have that variable first? Versus when you put the variable second, it tells you the opposite of this. And it has to do with what we're about to do. Yeah?
Tells you like to go left or right.
Tells you which way to shade. So if it's pointing to the right, you shade right. If it's pointing to the left, you shade left. If you put the variable right there, okay, on that side. So when we have a number line, just something like that, what kind of circle would this be? Open or closed?
Closed.
Closed on what number? Yep. And shade which way?
Right.
Yeah, right.
Shade in the direction it's pointing. Every number greater than or equal to 2. Okay. How about this one? First, do we agree that this and that are the same or no?
Yes.
They are the same. Which one, based on what we just did, should we go with?
Why is this?
Go with the second one, the one on the right. What kind of circle here? Open. So open on what number? 3. And shade which way? Yeah, shade to the left. Okay. Is that new for anyone, that kind of graphic? Shading? Okay, I didn't think so. This might be new. Our book does it a little different. Instead of using an open and a closed circle, they use a bracket. Now, the only thing about the bracket is you have to face it the way that you want it to shade. So not like an open circle where you can just put the circle and you don't have to think about it. You kind of have to think about which way the bracket's going to open. So x is greater than or equal to 2. You would put a bracket like this, and you would shade right. That's what it would look like. I don't care which way you do it. I'm just letting you know you might see both ways. So like if it's a multiple choice test and it said which one is correct, don't get confused by the bracket. It just means closed circle. And if we use a bracket for a closed circle, do you have a guess what we might use for open?
Parentheses.
Yeah, parenthesis. Same deal. You just have to make sure you have it facing the right way. Which way would the parenthesis face this time?
To the left.
To the left. And then you shade this way. Some teachers say you have to shade above the line. I don't care. You can shade above the line or right on the line. That doesn't really matter. Okay. So that might be a little different, but that's what you probably would see in our book. Short answer question on a test. I don't care which way you do it. Any question on that? Okay. Absolute value. Well, if you want to think about it as a distance, it's basically the distance from 0 on a number line. That's how a lot of people think of it. And since it's a distance, what kind of number does distance always have to be?
Positive.
Yep, it's always positive. So you can kind of break absolute value down into 2 different cases. If I give you a number that's greater than or equal to 0, what do you have to do to it to get its absolute value? Nothing, right? If I give you a number and say, what's the absolute value of the number? Just give me the number. If it's already greater than or equal to 0. Now, what do you have to do if I give you a number that's smaller than 0?
That's inverse.
Right, you take its inverse. If I give you a number, like say you had -3 inside here, and I say, what's the absolute value of negative 3? Take the inverse of negative 3. What does that mean technically? It means this. That's the inverse of negative 3. Negative 3. Which obviously is what number?
Just 3.
Just 3, yeah. Okay. So, real quick, absolute value of 6. 6. Absolute value negative 3. Absolute value of 0. Just 0. How far is 0 from itself? It's not 0. Okay, so if you had a number line spot here, another spot here, and you want to know how far apart those two spots are, what operation would you use to figure out distance between two spots on the number line?
Subtraction.
Yeah, you just subtract them. And because it's a distance, it doesn't really matter, like, I don't know, if this was 0 and this was 8. Well, you can do 0 minus 8 or 8 minus 0. They're 8 units apart. It doesn't matter which way you measure it. It's like measuring the distance of this table from left to right or right to left. It's the same thing, right? But you just make sure if you measure, and it comes out negative, distance is always positive. So, how would my expression look to find the distance between negative 2 and negative 9? I set up the template. But what would I plug in for A?
9.
Negative 2.
Sure, plug in negative 2, that's fine. And what would you plug in for B?
9.
Negative.
Negative 9. Okay. Because you're finding the distance between negative 2 and negative 9. What is the distance between negative 2 and negative 9?
7.
7. Right? If you do that out, that's negative 2 plus 9. And then the absolute value of that is, the absolute value of 7 is 7. So, two-dimensional coordinate system. Is there anyone that's not really familiar with XY axis? So X is your horizontal, Y is your vertical. What else? Quadrants are numbered 1, 2, 3, 4, going counterclockwise, starting in the upper right. Right is positive and up is positive, which means down is negative and so is left. What's another name for a coordinate? It's actually 2 words.
Point.
Okay, point, yeah, you could also think of a point, or there's one other name for a coordinate. No. Think of, does it matter if you switch X and Y? Like 3, 2, and 2, 3? So what's important there? The what?
Order.
Okay, so go with that.
Ordered pair.
Ordered pair, there we go, nice. Ordered pair. In a 3D coordinate, you call it an ordered triple. But since it's only 2, pair is 2. Ordered pair. Right. So we did actually get to zooming. I'm not going to have you get your calculator. I'm just going to show you how you zoom. So the reason why you might have to zoom is because, let me draw something like this. Don't worry how I'm drawing it. I'm just going to show you how to zoom. X squared plus 10. That's a parabola. Right? X squared. So if I draw it, and you set your window to, if you press zoom and you press 6, that's called a standard window. Standard window is always negative 10 to 10 on the X, negative 10 to 10 on the Y. It's like a starting point. Well, the little yellow circle was spinning in the upper right. Where's my parabola? Does anybody see it? It's off the screen. It's been shifted up 10 units. How would you know it's been shifted up? Well, we're going to learn how to recognize that by looking at the equation. So, if you press the window button, you can change where you want your axis minimum and maximum to be. So, this is x min, x max, y min, y max. That's always the order. X min max, y min max. So let's put them in. -20 to 20. And most of the time, this is something you have to figure out. I mean, they may give you a window to practice, but a lot of times you need to figure out what your window should be. And there's more than one right answer. Basically, the answer to this one is find me a window that shows me the parabola. Yeah, I'll take that. That looks good. It's decent. I mean, you've got a lot of space down here that you really don't need, so maybe you don't need your y minimum all the way at -20, but that's fine. So that's how you change your window. You just press window, and you can type in anything you want. Don't worry about x scale and y scale. Just worry about those 4 values right there. Okay, so if you really want to know what the scale does, not much. Look at how it looks now. Now let me change the x scale to 5. Does anybody see what changed? Just change the tick marks. So instead of putting 1 every unit, it just puts 1 every 5 units. What's that really important for? It isn't. I'll probably never play with that all year. You don't need to. So that's all you have to know for that. Just press window. And you can change it. The very last thing we'll finish next time, which is just the distance formula. How many people remember that from Algebra 1? A little bit? If not, that's fine. I'll give you the distance formula next time, and then we'll do one example finding the distance between 2 coordinates. But that was the last thing in that section. So we definitely went through that quick, but I hope, other than maybe like the zoom and like the idea of closure, I hope distributive, x-axis, y-axis, greater than, I hope all that was review. Is there any of that people hadn't seen? No. Okay. So next time, I'll let you play a little more with the graphing calculator, and we'll finish this up. And make sure you come here tomorrow before the assembly, unless they tell you otherwise. But I think they're going to have you come here first, and then we'll go down to the assembly at 12:30, and then unless they go right from the calf, but otherwise we'll do that, and then I'll probably have you bring your stuff, just in case we don't come back. Okay. But if we do, the only thing we have to really finish is distance formula. That's tomorrow. That one slide right there. That's all I have planned. So I'd give you the rest of the class after we go over that. You'd be able to work on homework tomorrow.